Ma'am, your voice is not clear, ma'am.
Now is it okay?
Now okay, ma'am.
Yeah. You tell me where you have stopped in the last class. I think you discussed about the differences between the soil organic and the inorganic colloids. Am I right? So this is live.
No, ma'am.
This is finished.
14 slide.
40th.
Yes, ma'am.
So that means this is finished, no? So I hope with that the classification is of soil colloids are over, right? Okay. So now we will just review the lectures up to soil colloids, right? Now is it clear for you?
Yes, ma'am.
Yes. What was the last lectures? About up to 9:30?
Biology.
Biology. Yeah, still people are not joined, no? There are 63 members. Will they come?
Yes, ma'am.
Okay. So today, please inform them also. Right. Otherwise, I will call the numbers AG035. AG035.
Yes, ma'am.
Yes. Can you please explain me what is soil colloid?
Okay, ma'am. Soil colloid means which have a particle size less than 1 micrometers. It's usually negatively charged.
Okay.
And it present mainly in active part or live part of the soil.
Okay. 044.
Yes, ma'am.
Yeah. What are the importance of studying soil colloids?
Soil colloid, it is essential for the essential nutrients, ma'am, because it holds many nutrients.
Okay.
Because of that negative charge. Without the soil colloid, we can't do the
exactly. Since it is having the
it's
negative charge
difficult,
on
ma'am.
the
The plant
surface.
can't grow.
Yes, it can attract the most of the positive charge cations. So those are the plant nutrients, right? So by attracting that, so it may reduce the leaching of these particular nutrients. Okay. So then 057. What are the general properties of soil colloids? 057.
Yes, ma'am.
Yeah, general properties of soil colloids.
Size, surface area.
What about the surface area of the soil colloids?
Surface area, small size and surface area have a large amount of outer surface.
Colloids are very small size, therefore it has the large amount of surface area in the external surface, right? Okay. Any other property?
Charge of surface charge.
069. 069. 069 absent, right? 082. 082.
Yes.
Okay. Can you please classify the soil colloids? Zero 082. 082.
Organic colloids,
Okay.
inorganic colloids, In inorganic collates, layers, silicates, iron and aluminum hydroxides, alphon and other amorphous minerals.
Okay, allophane and other amorphous minerals. Right. Then
In layer silicate, 1 type, 2 type, 2:1 type.
1:1 type, 2:1 type, and not 1 type to 1 type, right? 1:1 type. It is a proportion, right? 1:1 type, 2:1 type, and 2:1:1. Other name for the 2:1:1? 2:2 type, right? Yes. Then how to classify them? 2:1 type again. 082.
Limited expanding,
Okay.
non-expanding, and expanding.
Okay. Expand. Right. Good. 095. 095. AG095 absent, right? AG111. AG111. Rebel 1. AG111 absent.
Yes, madam.
Yeah. Okay. What are the building blocks of layer liquids? Building blocks of layer liquids.
Madam, can you repeat it?
What are the building blocks of layer liquids?
Silica tetrahedron and aluminium octahedron.
Yes. What do you mean by silicon tetrahedron?
Silicon tetrahedron mean one silicon atom is surrounded by 4 oxygen, and aluminium octahedron mean one aluminium atom is surrounded by 6 oxygen.
Okay. 099. 099.
Yes, madam.
Yeah. What do you mean by dioctahedral and trioctahedral?
Dioctahedral mean the silicate layer sheets are dominated by magnesium.
Which seat? It is an octahedral. Dioctahedral means so aluminium in the octahedral sheet dominated by what?
Aluminium.
Yeah. If the octahedral sheet is dominated by aluminium, that is dioctahedral. Then trioctahedral.
It is dominated by magnesium.
129. 129. AG129. 014. 014.
Yes, ma'am.
Anti-minor assignment. Example for 1:1 type of clay. 129. Sorry, 014.
Kaolinite.
Okay. How the 1:1 type of clay form? How does it form?
It contain one silica tetrahedron and one aluminium octahedron.
How it's formed?
It forms by oxygen bond.
Okay, the tetrahedron and oxygen, silicon tetrahedron and aluminum octahedron is linked by the oxygen bond. How the adjacent layers links together?
Hydrogen bond.
Yes. What are the properties of 1:1 type of clay? 006. 006. AG006. Yeah. What are the properties of 1:1 type of clay mineral? Less plasticity, stickiness. I don't hear you, please. Less plasticity, stickiness. Shrinkage and swelling. Also less. And the water holding capacity also less. What about the cation exchange capacity? The cation exchange capacity is low, ma'am. Low. Why? Because why it is low? Because the isomer substitution is little. Isomer substitution is little because of. So they can't. Okay. Because of strong hydrogen bond, right? Cation exchange capacity is low. Therefore, these minerals due to the low cation exchange capacity because of the little isomer substitution. Understand? Right. Then 020.
Yes, ma'am.
How the 2:1 type of clay minerals form?
One aluminum octahedral sheet sandwiched between two silicon tetrahedral sheets.
Two silicon tetrahedral sheet. Okay. What are the classification of that 2:1 type?
2:1 limited expanding type. Expanding type, limited expanding type, and non-expanding type.
010.
Yes, ma'am.
Example for 2:1 type of expanding minerals.
Smectitis.
Smectites.
Smect.
Okay. There are some properties of 2:1 expanding type of mineral.
They have high cation exchange capacity due to the high isomorphous substitution, and there are commonly appeared when drying. There are white cracks commonly appeared in this type of clay, and also
028. Okay. 028. AG 028 absent?
Yes, ma'am.
Yeah. So which one is having high cation exchange capacity? Vermiculite or smectites?
Smectites.
Why smectites?
Because it have high cation exchange capacity.
Others agree to this? Is smectites having high cation exchange capacity than vermiculite? Any other objection for this? Anyone please answer me whether the smectites or vermiculite having high cation exchange capacity? Anyone please?
Vermiculite, ma'am.
Who is this? Number please. Please answering me.
044, ma'am.
Okay, 044. The vermiculite example for which type of mineral?
2:1 limited expanding.
2:1 limited expanding type. Yes. Why vermiculite having high cation exchange capacity?
Aluminium, the magnesium along with the water molecules, ma'am. So the because of that, the minus charges are very high.
Yes.
The silicon ion substitute by the aluminium ions.
Yes, exactly.
So that it creates more positive charge.
Among all other silicate clay minerals, vermiculite have high cation exchange capacity Why? Because of considerable isomorphous substitution of silicon by the aluminum ion. Right? Because of that, it has the high cation exchange capacity among all other layers clays. Understand? So compared to the snack types, vermiculite have the high cation capacity. Okay, right. Where is other people? Only 61 members are joined. Where is others?
Some areas a power cut issue.
Half of the population have the power cut issue today. Only 61. At the beginning of lectures, there are 69 people joined. Now only 61 is there. Where is others? Hmm? How do you know that they have the power cut issue? The person who answered now, can you please tell me, how do you know that they have the power cut issue?
In front of me.
Hmm?
In front of me.
Yeah, I couldn't hear you. What happened? Hmm?
In front of me.
They informed to you?
Yes.
How they inform? Through the mobile?
Yes, ma'am.
Around 60, more than 60 people, they have the power cut issue. They inform. Hmm? Honestly, tell me, please. Anyhow, they have the mobile phone. No, they can log into the Zoom and they can join the meeting. No, still they have the power to inform you, so they can join in the meeting. No. Hmm? Can you please forward those messages to me? If they really inform to you, you just forward those messages to me. Then I can show it to the head of the department and get the special permission for them. Otherwise, more than half of the population is not there. Then how can I continue the lectures? Honestly, 0.5, 30, 30. Yeah, examples for organic life. 30. Please talk to me. Yeah. No, the humus is an example for organic life, right? Am I right?
Yes, ma'am.
Yes, ma'am.
30. Please talk to me, right? So, what do you think humus? What do you mean by size humus? Anyone?
Can you repeat the question again, ma'am?
Yeah, what do you mean by humus? No idea? Size humus, really, listen to me. Size humus is the end product of the decomposition of organic materials. Right after the decomposition of organic materials, we get the end product, that is we call as the humus. Right? It is the powerhouse of the nutrients. Okay. So here under the organic life, you may study that this humus is formed through the breakdown and the alteration of residue. So through the microbial activity, and also it may synthesize the new or more stable organic compost, that is the end product of decomposition of organic matter. Normally the organic matter decomposition is happen due to the microbial activity, right? So at the end, it produces the humus. This is more stable, it will not undergo for further decomposition. Right? So please 0. Okay. Zero, 4, 8.
Yes, ma'am.
Yeah, what are the differences between organic and inorganic colloids?
Organic colloid derived from decomposition of organic matter. Inorganic colloids derive from weathering of rocks and minerals.
That's okay.
Organic colloids contain carbon, hydrogen, oxygen. Inorganic contain Al, Si, Mg.
Al, aluminum, silicon, magnesium, and
Oxygen.
iron or oxygen they contain, right? Okay.
Organic colloids have high cation exchange capacity. Inorganic colloid has less. Organic colloids are amorphous in nature. Inorganic colloids are crystalline in nature.
Mostly these organic colloids are not stable ones. They can change. They are very dynamic, but the inorganic ones are stable ones. Right?
Oh, yes.
So with that, you are very clear about the organic and inorganic colloids. What is colloid and what are the classification and the properties of each classification, each type, right? It's very important. Then only you can easily understand about the charges. Right? Now we are going to start about the sources of charges on clays. Right? Sources of charges on clays. So far we discussed about what are the actually the properties and what are the charges are there. What is the tetrahedron and the octahedron sheets. Okay, so based on that we are going to discuss about the charges. What are the charges are there? What are the sources of charges of this place? Can you all see my slides now?
Yes, ma'am.
Okay.
Yes, ma'am.
Normally, there are two major sources of charges on the soil colloids. Okay, one is pH dependent charge, that is the variable charge. So it is a dynamic one. Okay, and the other one is the pH independent. When the pH is changed, it will not change. It is we call it as the constant or the permanent charge. Okay, the pH dependent charge, when the pH is fluctuating, the charge also fluctuates. But in the pH independent charge, it will not depend on the pH. Whatever the pH, the charges remain permanent. Okay, so this pH dependent or the variable charge due to the ionizable OH and the protonation of the hydrogen of the H plus signs. Okay, the pH independent charge or the permanent charge mainly formed due to the isomorphous substitution. So it is not depend on the pH. pH, you know, basically the OH minus and H plus, right? Concentration, negative logarithm of the H plus concentration, right? When the pH, the H plus and the OH minus changes, the charges also change. That is the ionizable OH minus and the protonation of the hydrogen ions. But it's the isomorphous substitution, you know, basically substituted by the same size of ions substituted in the similar ions without changing the structure, right? So that is the isomorphous substitution. When the pH is changed or not, it will not change. It is the permanent one, right? So here that is what we call this as a hydroxide. So the functional groups on the surfaces. These are the functional groups. You know, in the organic colloids, there are some COOH groups, carboxyl groups, aldehydes are there. So they may create the charges like COO minus. So it can then accept the H plus ions. So that create the charges there, right? And the second charge is the charge imbalance. That is the isomorph substitution we call, right? So here, obviously, there are two sources. One is the pH dependent one, or the variable charge. Another one is the pH independent, or the permanent charge due to the isomorph substitution, right? So first we will see about what is isomorph substitution, right? As I said earlier, during the weathering of the primary minerals dissolve and recrystallize as a secondary mineral. During this process, one element may become substituted for another element of similar size in crystals. It's very important. Similar size element in the crystal structure without changing the shape of the crystal. That is the isomorph substitution. One element may become substituted for another element of similar size in the crystal without changing the shape of the crystal. Anyone please repeat me, what is isomorph substitution? This is important definition. So you can add this also, but this is the definition. Anyone please repeat me? If you really understand, please tell me what is isomorph substitution by looking at the slides, no problem. You can tell me. Go through the slide and tell me. I should know whether you understand or not. What is isomorph substitution? Simply, one element may become substituted for another element of similar size in the crystal structure without changing the shape of the crystal. That is the definition. Anyone please repeat me. Then only I will move to the next.
One element may be
Yes. Who is that? Person who talk now, please.
Yes.
Yes. Yes, sure. You can.
One element may become substituted for another element of similar size in the crystal structure without changing the shape of the crystal.
Shape of the crystal. That is the important points in the isomorph substitution. Then you can add some more points. It happens during the weathering. Their primary minerals may be dissolved and recrystallized as a secondary mineral. That is the additional point. Right? But this is the important one. Similar size without changing the shape of the crystal. Process of replacing silicon in the tetrahedron or the aluminum in the octahedron by other ions of comparable size without changing the basic structure of crystal is a substitution. You can give this definition also. So this is a real definition. So you can add with the example. Replacing silicon in the tetrahedron or aluminum in the octahedron. Kind of example, right? If the two elements do not have the same ionic charge, then an unsatisfied negative charge remains at the point of the crystal. If we are replacing one element by another element, if those two elements do not have the same ionic charge, for example, if one is having the 4 plus or if one is having 3 plus, there should be the net unbalanced charge. Okay, that will create the unsatisfied net charges. So that will remain in the crystals. That will form the sources for the charges. Okay, so if both ions are same in ionic charge, definitely that will be balanced. So that will not create any charges. Okay, so there is an unbalanced charge because of the elements do not have the same ionic charges. Right? Here we see how the charges are formed. Right? See here, what is this one? Tell me, what is this? Can anyone please look at the slide? Can anyone please explain me how this is formed? Or explain me about this thing. 164, can you? You refer the slide. I will give you the time to refer the slide and you explain.
Okay.
Tell me first, what is this sheet?
Trioctahedral. Yes.
Okay, why this is trioctahedral shape? Can you tell me?
Because dominator location.
Yeah, by magnesium ions, this is 2 plus ions because it is, so therefore it is dominated by the magnesium ions. There are 3 magnesium ions to satisfy all the charges, right? That is what this is the trioctahedral. Okay, here the net positive charge is 6. Okay, that's clear. Positive charge is 6. Net negative charge. What is this one? What is this element?
Oxygen.
Oxygen is there. So why there is a 3 negative charges? Why 3 negative charges? One negative charge almost shared here, right? Understand? One negative charge almost shared here. So there are 3 net negative charge. Understand that?
Yes, ma'am.
Or oxygen having 2 minus. So one is almost shared with the magnesium. And now it is having 1. Likewise, 3 oxygen atoms having the 3 negative charge. Okay. Here also 3 negative charge. Okay. So together in the sheet, trioctahedral sheet, net charges
0.
0. While 6 plus and 6 minus. Then net negative charges 0. Is it clear? Clear? 164?
Yes, ma'am.
Clear?
Yes, ma'am.
Okay. Can you now explain this one?
This dioctahedral sheet.
Okay. Why this is dioctahedral shape? Others, please listen. Huh? Yes. He is the one going to explain this one. So I will not repeat. So therefore, it is, others, please listen carefully. Okay. You continue.
If it's dominated by aluminum sheet,
Yes.
so the central element is aluminum.
Aluminum.
So 3 plus.
Okay.
And side elements is oxygen.
Okay.
So there's 2 minus. So one is joined with aluminum. So negative charge is 3 minus. So like that under 3 minus. So net charge is neutral, 0.
0. Right. Here without isomorph substitution, right? So net charges are 0, right? In the trioctahedral sheet and in the dioctahedral sheet. So without any substitution, this net charges are 0. Okay, we said that in the previous slide, isomorph substitution is the reason to create the charges. Understand that? Now, what we are going to see is how this isomorph substitution is going to create the charge, net charge. Okay, see here. Anyone, please, any others, can you please explain this one, how the isomorph substitution is create the charges? Any volunteers? Any volunteers? You are welcome to explain it. Six four, can you? 164, can you? Any idea?
Magnesium, dioctahedral and trioctahedral.
This one is trioctahedral without any substitution. This is the dioctahedral without any substitution, right? Here, dioctahedral sheet. Why it is dioctahedral sheet? Because 2 ions are there, right? 2 center elements sharing the 6 oxygen atoms. So that should be 2. If it is 2 center elements, that is should be the aluminum 3 plus. So therefore, it should be the dioctahedral sheet. But what is happening here? One aluminum ion is substituted by the magnesium. Right? Understand?
Ma'am.
Others understand?
Yes, ma'am.
Yes. Yeah. If you have doubts, please ask me, right? So this should be, while looking at this sheet, you can tell that this should be the dioctahedral one because two center elements are satisfying with these 6 oxygen atoms charges, right? But the partially or the one aluminum ion is substituted by the silicon ions, right? That is the isomorph substitution. So this isomorph substitution definitely will create the net negative charge. Why? So here the center element's net charge is 5 plus. Okay. Anyhow, the apical elements charges are 3 minus. Understand that? As usual, this is shared. One oxygen should be shared here. So there should be the 3 minus and 3 minus. There should be the 1 minus. 6 plus, it should, if it is 6, 1, then no negative, no charges. No net charges, right? So since it is the 5 plus, by substituted by the magnesium, there is a net negative charge. Understand? Understand? Yes. So that is the isomorph substitution is creating the net negative charge. Okay. So this may attract one positive ion, okay, and can fall with them. So that is how the academic sense processes happens due to the isomorph substitution. Definitely, if it is having the negative charge, it should attract one positive charge ion, right? Understand this? Any clear? We said that isomorph substitution is a reason to create the charges on the soil colloids. So that is what we discussed here. This is the pH independent. It will not depends on the pH because it is truly depends on the isomorph substitution. Substitution of one element of similar size by other element of similar size and without changing the shape of the structure or structure of the, without changing the structure of the sheet. Right? So that is how the isomorph substitution create the charges on the surface of the colloid. Any doubts up to this? Any doubts? Are you all clear this one?
Yes, ma'am.
Only 2-3 people are responding. Others are, you do not open the mouth. Why? 057. Is it clear?
Yes, ma'am.
057. 57. You are no?
Yes, ma'am.
54.
Yes, ma'am.
Who is 57? I don't hear most of the boys' voices.
I'm not a boy.
Yeah, I understand. So only 164 is answering me. Any others, please? I should at least remember the numbers, then only I can call them. Any boys, please? Please tell me whether you understand or not. Please tell me, at least tell me whether you understand or not.
Yes, ma'am.
At least 082. 082?
Yes, ma'am.
Okay, any others? Any others? There are some people that talk, no?
Yes, ma'am.
Yes, ma'am. I understood.
164, okay. And any others? Yeah, 090. Any others?
Yes, madam.
030. I should catch now.
Yes, ma'am. Understood.
039. Others?
Yes, madam.
39. You are no? Yes. Any others?
Yes, ma'am.
108.
Yes, madam.
Yes, ma'am.
Okay. Okay, thank you. I should catch up with some boys' numbers, right? Then only I can ask the questions in the next class, right? Okay. Thank you. Thank you for giving your with the numbers, right? Okay, now we'll move to the next slide. I hope that it is clear for you. What is the next lecture?
Economics.
Economics.
Economics, right? Yeah, again in the text, you should understand this. Common substitutions are Al3 plus for the silicon. Okay, if it is the silicon is substituted by the aluminum, you can from the sentence you can even understand, right? There should be the net charge, right? Again by magnesium substitute for aluminum substituted by the magnesium, there should be the one negative charge. Here also one negative charge again, and aluminum may be substituted by the iron, right? This is how in the substitutions occurs in the octahedral sheets, right? By by the ions you may understand that where it should happen, right? And each leaving a net negative charges of the crystal. Here 4 plus substituted by 3 plus, there should be one negative charge. Again 3 plus substituted by 2 plus, there should be one negative charge. Again 3 plus substituted by 2 plus, there should be one negative charge. So each leaving a net negative charges on the crystal. So this charge does not depend on the pH. Whether the pH fluctuates, it doesn't matter. Okay, because this is not depend on the pH. That's the permanent charges or constant charges. Therefore, we call it as a permanent or the constant charge. If the questions comes about the permanent charge or the constant charge, you should catch up that it should be about the isomorphic substitution, right? So here the substitution of aluminum for magnesium or the silicon for, so aluminum gives the positive charges. Okay, understand why positive charge? The 2 plus is satisfied by 3 plus. There should be one positive charge. Here 4 plus substituted by 3 plus. So there should be one negative charge. But here 2 plus substituted by 3 plus, the charge, lower charge one substituted by higher charge one, definitely there should be the positive charge. Okay, understand that? Here the higher charge one substituted by lower charge, there should be the one negative charge. I hope it is very simple, no, very basic thing. And the second thing is the exposed hydroxyl groups or other functional groups on the surface of the clay crystals. They can release or accept the H plus or the provide either negative or the positive charges. This accounts for most of the net negative charges in the kyolinite and some of the charges in the monolinolite and the vermiculite and elite. Okay, see here, I will explain this how it happens in the next slide, right? Some of the clay minerals, they may expose this, the H plus, they can accept the H plus ions or they may provide the H plus. Okay, by that it can create the net negative charges. Okay, here you know in the kyolinite, the isomorphic substitution is not there, right? So because of that, even the cation exchange capacity also low. And then the broken oxygen bonds at the edges of crystals. So during the weathering process, okay, sometimes these minerals may undergo or may be exposed to the weathering. Therefore, the apical charges maybe the oxygen may be partially better, and the aluminum or the silicons may be exposed to the environment. So that may create the net charges. So here at the broken edges of crystals, the small Al3 plus and the Si4 plus silicon ions are exposed to the weathering and may be lost. That is the reason of the broken oxygen bonds at the edges of crystals. So therefore, the remaining oxygen ions have an unsatisfied net negative charges. This is an important source for the charges in all places. Understand this? Due to the weathering processes, so if the edges are broken due to the weathering, the aluminum or the center ions may be exposed to the weathering and they may be lost. Because of that, so the remaining oxygen, the apical oxygen, may have the unsatisfied negative charges. Understand? Understand this?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Now we see what is the variable charges. pH dependent. So once the pH dependent means once the pH is changing, the charges also may be changed. Okay, that is the variable or the pH dependent charges. Okay, so this charge is mostly associated with the colloids such as humus, allophane, and the iron and aluminum hydroxides. Because the humus, as I said, at the edges it may have the carboxyl groups, COH groups. Okay, due to the pH changes, this COH H plus may be dissociate or dissolve, and it may be changed with the pH. So therefore, the variable charges are mainly associated with the colloids such as humus, allophane, and other aluminum hydroxide, iron and aluminum hydroxide. So the hydroxides, whether crystalline or the amorphous, get their charge from the surface protonation and the deprotonation. You know what you mean by protonation and the deprotonation, acceptance or the rejection of the H plus ions, respectively, right? So the layers liquids have a small amount of variable charges because of OH at the edges. Okay? Variable charges are very low in the layers liquids because the OH minus in the edges. So all these negative charges on the humus is variable. Why? In the edges it may have the COH groups. Because of that, all the negative charges on the humus is pH dependent or the variable charges. Here the hydroxide oxides are positively charged in some very acid soils and help to retain the anions. Here you can see how the negative charges are formed in the variable charges. So in both cases, in the permanent charge or in the variable charges, it may create the positive and the negative charges. You know how the positive and the negative charges are created in the permanent charge or in the isomorph substitution that I explained, how the positive charge formed and how the negative charge. Here, the higher charge element replaced by the lower charge one, so that create the negative charge. The lower charge one substituted by the higher charge one, that creates the positive charge. It is in the permanent charge. Likewise, in the variable charge also, so this may create the negative charge and also this may create the positive charge. So now we will see how the negative charges are formed in the pH dependent one. Are you all clear up to this? We are running out of time, right? So since you have a next lectures by 10:30 or 10:45.
At 10:30.
Really sorry, we are running out of time. So with this, I'll finish it here. So we'll continue in the next class by the Monday, right? If you have any doubts, please ask me, right? I will try to upload your notes. Okay, thank you very much. You can leave now.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.